In the final section for today, we will discuss how to evaluate our trained classifier. In particular, we will revisit our goal of estimating the true classification error. And related to that, we will discuss the phenomenon of overfitting to the training set and generalization. And this will require us in general to split our data into a train, validation, and test set. And we will discuss a proper standard machine learning workflow. And finally, we will shortly discuss the confusion matrix as a simple analysis tool to analyze the errors committed by our classifier. Okay, so let's say we have trained the classifier H. And recall, our data has been generated by some distribution P star over features and classes, and the data has been generated IID, independently drawn from this distribution and identically distributed according to this distribution. And recall that the overall goal is to estimate or to compute the true classification error. So classification error true, which is just the probability of making a mistake, or also the average number of mistakes on a very large test set. So the principal problem is, well, P star is not known to us. We assume it exists and we assume it produced our data, but we don't know it. And even if we knew it, computing these probabilities or this expectation is a computational hard problem in general. So the idea is now to approximate the true error with an empirical average, so from a finite sample. So say we have a collection of n samples and we simply count the number of errors within the samples. So this is the indicator function, and this is 1 when the output of our classifier for sample xi does not agree with the true label. And we average this by the number of samples. So using a finite sample, we can have a finite sample approximation of the true error. So great, we have all this nice training data. So can we use the training data to estimate the true error? And actually, this is a bad idea, and this is related to the problem of overfitting. So we will discuss the overfitting problem repeatedly in this course, and it's often best illustrated with a toy problem. So here we have a toy classification problem where we have only one input feature, a single dimensional input feature here on the x-axis, and we have two classes. So a positive class, these are these blue X's, and we have a negative class with these red circles. And now our machine learning model is simply of this one-dimensional function f, and we would classify the positive class when f is larger than 0, so larger than this threshold here, and otherwise we predict the negative class. And the machine learning model we consider here are polynomials, and it's well known how to fit polynomials. And now we could start to fit a degree 3 polynomial. So this is the minimum mean squared error fit. And we see it actually does a good job. So it seems that there are more negative samples on this side and more positive samples on this side. And it seems that maybe this positive sample here and this negative sample here are more outliers. And essentially this polynomial would decide, well, everything which is left of this point where it intersects the 0 line is negative class, and everything on the right is positive class. So this doesn't seem too bad, and maybe this is actually the true principle which generates our data. So if we now increase the power of our machine learning model, so by increasing the degree of our polynomials, then we would actually get this. So if we fit a degree 10 polynomial, this polynomial really goes wide in order to fit all these points exactly. So this green polynomial goes through all these points here exactly. So it makes 0 training error. So it classifies all the training examples correctly. And moreover, it even gets the numerical values of the encoded class labels, namely +1 and -1, exactly correct. So like it makes 0 error here. But we see by naked eye that this seems to be a bad classifier. So here it overshoots just to capture this positive point and say if it's really the concept that on this side there are more negative examples, all the examples here would be essentially incorrectly classified. And also here it shoots down to get this point, and essentially it would classify all these points here as negative. So if it's really true that on this side there are more positive examples, all these points would be classified incorrectly. So in a nutshell, this just means, well, the training error is too optimistic. So the training error is a too optimistic measure of the true classification error. And in particular, if we get a small training error, like in this polynomial 10, polynomial of degree 10, this doesn't really imply good generalization. So this doesn't really mean that we discovered the underlying principle which generated this data. So small training error does not really imply that the true error is also small. So this is generally known as overfitting or as bad generalization. And therefore, in order to estimate the true error faithfully, we actually need to do this on a different set, so on a reserved test set. And so in general, we would therefore introduce a training and a test set, but we will also introduce a so-called validation set, which I will illustrate here. So say we have some data of n samples, and these are illustrated here with this gray bar here. So first of all, we just saw we should actually divide all the data we have into a training set and into a test set. So this blue portion would be our training set, and this red portion would be our test set. The training set is in order to train our model, and the test set to estimate the performance or the true error. However, moreover, our algorithms typically have hyperparameters. For example, we had this smoothing parameter in naive Bayes, and we had various thresholds in decision trees. And in general, the more complicated our machine learning models become, the more hyperparameters we will have. So we will discuss more models in this course, and they have all their sets of hyperparameters. And we somehow need to set these hyperparameters. And a very simple and principled way to do this is actually to further split our training set into actual training set and a validation set. So the overall data is now split into a training set, a validation set, and a test set. And so training will be done on the training set, the validation set will be used to tune our hyperparameters, and the test set will be used to assess the performance. So now we have a hard decision how to split our data points into training, validation, test sets, and typical splits are like something like 60% training set, 20% validation set, and 20% test set, or 70, 15, 15. So now we have to deal with this trade-off, and I want you to shortly think about what are advantages and disadvantages of different trade-offs. So splitting our data into training, validation, and test set also leads to a good standard workflow for training machine learning models. So as said, our model has several hyperparameters, and we a priori select a suitable range for these hyperparameters or certain configurations for these hyperparameters. And now for each of these configurations, we would train a model on the training set. And of course, we can evaluate the train error, but as said, the train error tells us little about the true performance. So essentially, we would then pass on our model to the validation stage, and where we evaluate the error on the validation set, and we get a validation error. And as said, like we do this essentially for each setting of hyperparameters which we consider. And then after having done this, then comes the test stage. So we pass on the model with the best error on the validation set, and now at the final stage we are ready to test the model. So now we evaluate the error on our selected model, and we get the test error. And essentially now we are done. We have an assessment of the true error, and we cannot go back. So avoid the following situation, the human in the loop situation. What often happens is that you are disappointed with the test error, and you say, well, maybe I've selected a bad range of hyperparameters, or maybe I could have changed some other setting in the training procedure. So what if I had changed something in the whole training procedure, and you go back and do the same thing again, and then you test again? But essentially this is not allowed, since your decision has been based on observing the test error. So you were disappointed by the test error, so you looked at the train error, which was like pretty low, and also the validation error was low, but now the test error is high and you're disappointed and you go back. But that actually means that you leak information from your testing procedure, from the test set, back into training. So essentially, as soon as you do this, as soon as you have the human in the loop, actually information leaks from the test set into training. And this is actually forbidden. So this is bad practice if you do this. So to summarize the different errors we considered, we are actually interested in the true error, which is the ideal measure, but actually out of reach. We have the train error, which is the empirical error on the training set. And as said, this is overly optimistic. So we fit our machine learning algorithm to, or our machine learning model to our training data. And therefore the error here will be overly optimistic. It will be lower than the true error. Also the validation error, which is the error on the validation set, and which is used to guide our selection of hyperparameters, will be in general optimistic, since we are selecting a range of hyperparameters, and therefore this error will be actually lower. So we take the model with lowest error, and this will be also an optimistic estimate of the true error. So in some sense, we are, by selecting suitable hyperparameters, we are overfitting also to the validation set. And finally, we had this test error, which is essentially done on our test set. So, which is essentially now really a noisy estimate of true error. And key was that to keep the human out of the loop, so the test error must be secret, and we must test only once at the end. And then this is actually an unbiased but noisy estimate of the true error. So essentially the test error really tells us something about the true performance. And of course, this is a noisy estimate of the true error. However, if we actually got an infinite test set, then we would converge to the true error. So if we increase the number of test samples to infinity, then actually the test error, by definition, converges to the true error. Sometimes we report accuracy instead of error, and this is essentially the same story. So the only difference between error and accuracy is that in error, we count the number of misclassifications, so whenever the predicted class is not equal the ground truth class, and in accuracy we count the number of successes or correct predictions, so whenever the predicted class is equal the ground truth class. So accuracy and error, the same story, essentially just opposite of each other. So accuracy is always given as 1 minus classification error. And sometimes people report accuracy and sometimes classification error, but it's really the same story. And the last topic in this section, we discussed the confusion matrix here in terms of accuracy, so in terms of successes rather than error. And this is an analysis of our classifier, of the errors committed of our classifier here for a classical data set, the so-called iris data set, where the goal is to distinguish 3 different kinds of irises, so flowers, and there are setosa irises and versicolor irises and virginica irises. And the confusion matrix is a pretty simple analysis tool and simple concept. So it's a matrix where the rows correspond to true labels and the columns correspond to predicted labels. So for example, in this box, we see that there are 13 data items where the true label is setosa and the predicted label is also setosa. So all of these items were predicted correctly. Similarly, in this box, second row, second column, 10 items which are versicolor and actually have been predicted as versicolor. So again, all correct. And similarly in this third diagonal entry. And the off-diagonal entries, they count the errors. So we see that there are 6 data items where the true label is actually versicolor, but they have been predicted as virginica by our model. So it seems that our model likes to confuse versicolor irises for virginica irises. We can give this a nice color shading so that we can see in one view what kind of errors our model does. And here on the right-hand side, this is actually the same story, but just where the rows have been normalized to 1. So we sum over the rows and divide each of the elements in each row by the row sum, or by the sum over the rows. We see that the color encoding therefore is slightly different because here we had 9 and 13, and if we normalize, both of these become 1. But essentially this is the same story on both sides. So to conclude this section, we revisited the true classification error as the the holy grail. So that's essentially what we're really interested in. And we again emphasize that this is hard to compute and actually out of reach. And actually it's impossible to compute if we don't have the true data generating distribution P star. And therefore our goal must be to estimate it with a finite sample. And we again discussed overfitting, and that it's a bad idea to use the training data to estimate the error, because our machine learning model gets fit to the training data. It becomes typically overfit to the training data, and therefore the error committed on the training data is a bad measure for the true error. And we discussed a general good practice for machine learning training, so to split our data into a train, validation and test set, where the training set is there to train our model, the validation set is to tune our hyperparameters, and the test set is, really to test and to get an unbiased performance estimation. And recall, the test set is secret. You cannot use it for training, and avoid a human in the loop situation. So where you look at the test error, you're dissatisfied, and you go back to training. So this is actually forbidden, since that actually leaks information from the test set to the training procedure. And finally, we discussed the confusion matrix as a simple visualization of the classification errors. So a simple concept to analyze which kind of errors your model commits.